I'm Engineer Sanola Khaskeli, along with my groupmate, Engineer Mohammad Awais Javed. I'm here to present Sukkur IBA University Robotic Platform for Education project under the supervision of Engineer Dr. Suresh Kumar and co-supervision of Engineer Dr. Mohammad Mukhas. So, introduction. The project is to provide a cost-effective 3D human-following robot with built-in sensors for introduction to robotic lab and other research work, and to develop a platform that can be used in narrow space, having high efficiency regarding of cost as well as power consumption. The design robot is supposed to perform several tasks which may include following a line, solving a maze, avoiding obstacle, detecting light, so on and so forth. So motivation behind this project. Since we know there is no initial product available in the market, apart from this, we also want instant interaction with robot in order to develop interest in technology as well as to help them with a robotic platform and to enhance the creativity of students by different challenges like line following, obstacle avoidance. We also were motivated to design a hardware development and programming environment for students. So the objective of this project was to design a human-friendly 3D compact robot, which must include built-in sensors. It must be a customizable, cost-effective. It has to be a less power consumption, and it is supposed to help students in labs as well as research work. So the problem is still, we know that there are many robots available in market, locally as well as international level. So why we are designing basically this robot? So when we study literature, we understand that there are many problems which we are working to trying to mitigate. Is they are bulkier. There are robots which are difficult to wire. With them, there's a space issue with them. They need more power. They are difficult to troubleshoot. There is sensors losing, and they are costly. So all these problems we will discuss further when we describe the literature review. So solution. So what sort of solution we are providing? Basically, we are providing a 3D compact miniature size robot which contain all the sensors. It is power effective, easy to program, cost effective, customized, and reliable. Comparison with literature. As I have already described, there are a number of robots available in market, but here I am comparing them with few famous robots and also a locally available robot, which is current robot available at Sukkur IBA University robotic labs. So since you know the Show Robotics, which is Sukkur IBA University robotic platform, it has some features which I am comparing with others, like it's affordable, it is customizable, it's multi-purpose application based, it's compact, it has all the sensors built in and reliability, and it is way more easy to program as compared to other robots. Since we are using C language, which is quite easy even for students of schools and colleges. If we compare it with available robot at Sukkur IBA University robotic platform, robotic lab, or other institutes, they are affordable, but they are not customizable. They have limited applications. They are not compact. They don't contain all the sensors and reliable. Though they are simple in programming, but these are the issues which we have to mitigate. Likewise, in Show Robotics, it is way too complex to program, especially for the students of schools and colleges. Though it is reliable, it contain all the sensors, it has multiple applications, but it is not available at affordable. Likewise, M-board robot, it is a highly expensive robot. It is customizable, but it has limited purpose applications and not compact. It is also a bulkier robot, and although quite complex to program. Likewise, iRobot. So these are the challenges which we overcome in our project. So this was the flow diagram of our robots. This is how we will work on our robots. Basically, it gives us a blueprint. What we are going, basically a rough sketch of a robot. What sort of most important components which will be implemented, which are required. So here are battery, USB charging port, regulating circuit 3.3, which is battery management system indeed, motor driver, main controller, sensors module. It contains all the sensors and motor driver as well as encoder. It also must contain the Wi-Fi and Bluetooth module. So after the initial rough sketch, then we come across the placement of sensors. So this is also a rough sketch of our robot. It describes where we have to place the sensor. Since we are designing a robot which is a burger type, it contains 3 floors: ground floor, first floor, and second floor. So it is very important to describe which sensor is placed at what location in robot, so as to make it compact and less bulkier. So you can see that at the 4 sides of robot, like in front and back and left and right, there's ultrasonic sensors at front. There's additional thing is camera module, which is we are using ESP32 cam, the ultrasonic module, and IR top. Basically, we are trying to use ultrasonic as well as IR for different lab tasks. So we add both IR top as well as IR ultrasonic sensors in the side as well as the front and back. Then there's IR ground sensors. Basically, IR ground sensor is used to perform several tasks like line following robot, like maze solving of different colors. So likewise, we have 2 other LDR sensor which will be placed at the top floor, which you can say terrace of this robotic house. Then there is a microcontroller. Basically, we are using ESP microcontroller. The purpose of this choosing this microcontroller is that it contains Bluetooth as well as Wi-Fi module. Then there's a battery and battery management system. Then there's a GPS module for again for locating the robot and the finding the locations for other lab tasks. And then there is a stepper motor, which are highly recommended motors are stepper motors. So component, as I have already described, we are using these components including IR, ultrasonic, GPS, LDR, so on and so forth, which I have already described in previous slide. So these were the component selection. Now, what sort of lab we will perform? That's important. So these are the lab tasks or challenges which a student is supposed to perform with our platform, with our robotic platform, including the designing a basic mobile robot, which should be like moving it to a left or right, or backward or forward. So next lab is to perform in this lab, robot is supposed to avoid obstacle by sensing it from using sensors like ultrasonic sensor or IR sensor. Then there is a line following, then there is a maze solving, remote control robot, GPS locator, surveying robot, hand following, light seeking, sumo. We can perform number of other labs as well. Since this is a program controlled, so what sort of program you can use? You can perform the tasks like with ultrasonic sensors. You can perform many other tasks like with the camera. You can perform many tasks, including face detection, including camera recorder, so on and so forth. So the methodology, that's very important part I'm describing here. Perhaps we have 4 parts in this case. There is a software part, there is a hardware part, there is assembly, and there is a testing. So in software part, we have to design libraries. We have to design its 2D and 3D part using SolidWorks or CAD softwares. We have to design PCBs in order to get printed. These all things come under the definition of software. Then there is a hardware. In hardware, we have to get printed form, or you can say hard form of these sensors, these components and these parts. Then we assemble them, and then at final we will test them. So purpose 3D model. This was basically the first purpose 3D model we presented. As I have already described, it has 3 floors: ground floor, first floor, and top floor. You can see that there's a ultrasonic sensors placement there. There are 4 ultrasonic sensors. There are IR sensors. There are motors and coaster ball. Again, there is a motor driver. There is a battery and battery management system. It was recommended from my groupmate, Mr. Aves, engineer Aves Javed, that microcontroller should be placed at top, but with the study of environment, come to know that no, we cannot place it at top, but inside the top module. So you can say microcontroller placed there. There are LDR sensors. So I will describe their placement and actual how we describe later in next slides. So then software part. In software part, we have designed different ESP, including main circuit board, motor driver, LDR circuit, IR circuit. So you can see these all are the Eagle PCB design, just a CAD software we use to design these PCBs. Then we get hardware circuited. We sold them. These circuits are printed using a Sukkur IBA University Fab Lab, which is fabrication lab. It's quite interesting to see how these circuits get printed. Then soldering is another technique. It's a learning. It's quite important for learning. Then there's IR sensors. So you can see we all doing all these things here at Sukkur IBA University Fab Lab, fabrication lab. It's quite good environment there. Then there is a parts of 3D. You can see we recommended, it was recommended use a stepper motor, but due to COVID and other pandemic issues, we didn't get that motor from China due to delivery issue and due to lockdown issue. So we switched to DC encoder motor. Then we realized, no, this will not work. We have to switch from DC gear motor. And this is, here we are describing the holder, motor holder we design using SolidWorks. Then there is a battery holder. Then there is a ESP camera holder, then battery holder, sensors holder, like ultrasonic and IR sensors holder. So these are printed here at Sukkur IBA University Fabrication Lab. Then there's the assembly, which is third part of our methodology. We have assembled robot from here to here. Basically, this was the basic, as I have already described, that we switch to gear DC motors, which are shown here. Then there is this basic robot base. Then there is a bumper, 3D bumper for sumo robot. This is also designed using SolidWorks. This was quite complex, but it's all depend upon our skills. Then this was this first floor, and you can see that there are number of sensors built in, embedded here, like ultrasonic sensors and IR sensors. Then main board, the most important part. This is the final assembly with camera, with GPS antenna, with dip switches, power switches, micro USB. So this was the whole assembly. Now I am describing which sensors we are, describing the components as shown in previous figure. This is ESP camera, this is GPS antenna, LDR sensors are placed here. Then this is a power switch button, this is programming port, micro USB programming port. Dip switch is used for redundancy purpose. In case secondary ESP failed, we can control the power of different sensors using dip switches. Then there is IR sensor top, IR top sensor, then ultrasonic sensors, and sumo bumper. This was the internal structure, including IR ground sensor, DC gear motor, battery management system is there. There's a motor driver and boost converter. Basically, we are using lithium-ion 3.7 volt battery, so we need 5 volts for motor. In order to boost them, we use a boost converter. Then result, the testing. As I have described the methodology, we have fourth part is to test the robot. So we have test on several lab tasks. We give several challenges to robot and test them accordingly. So you can see in this graph, it is shown that the robot is performing forward and backward movement. So you can see this was the desired path for backward and forward movement, but there is a slight deviation. It's about 4.5 degree deviation from the actual point. This is just because of the gear motor, as I have already told you, the recommended motor was stepper motor, but these are the gear motors. So there's a slight, you can see there's a slight deviation. One is moving faster than others. So because of that, and there's also issue of vibration. That's why robot is slightly deviating from its actual path. Then we perform obstacle avoidance robot. In this robot, we program it in a way that it avoid obstacle 10 inches before the obstacles. It has to sense the obstacle, then it has to turn left 10 inches before the obstacle. So you can see this was the expected path, desired path, but due to latency delay and due to deviation in motor, it get data a bit delayed and turn after 2.5 inches. It take 2.5 more inches, and I will also show you this in video. So how it is not performing the actual, not doing its task actually perfectly, just because of the deviation. Because in practical work, there is always some little issues of deviations like troubleshooting. So these are the practical parameters. This is ideal line, but practically it's slight deviation. So the third task which we performed is line following this. You can see there's a U-shaped path which is robot has to follow, but due to vibration and due to slight deviation, robot was deviating again and again and coming back to line. So you can see it's like a sine wave, and then it circulate and then it stopped there. So this was the actual path was described, and this was the desired path, and this was the actual path robot formed. Then the fourth level we performed 4 tasks was to light seeking. Basically, at 2 different locations, we place 2 light source, and we program it in a way that if light intensity is with a specific light intensity, robot turn left. If intensity increases, it has to turn right. So we see it follow the command from microcontroller, but there was a slight deviation and there was a slight, you can see, delay due to actual parameters. Actually, things doesn't work like we want. These are the ideal cases. So it shows the actual, you can see result of our robot. Then how we achieve objectives. At the first I described 5 different objectives. So now I am going to show you how we achieve all these objectives from 1 to 5. So let's go to first objective. The first objective was to design a 3D complete robot. Here it is. You can see it's a complete package. Then the second objective was it must contain all the sensors which I have already described. There's all the sensors in this. So this was how we achieve our second objective. Then third objective was the cost analysis, which you can see here. Our robot is very is quite you can see available at affordable price. It is available at low cost. Then the fourth objective was to power effective. So I've already described we are using two different microcontrollers. Now, since we know when we embed all the sensors as microcontroller, they always get power from microcontroller. So in order to make it power effective, we have to design a mechanism. So here we are using two different microcontrollers. One is primary and second one is secondary. The primary microcontroller, the purpose of primary microcontroller is to get data from sensors like input, output. But the purpose of secondary microcontroller is to activate and deactivate all the sensors according to desire, according to our need. So we design library, we send Boolean functions like true, false, the number of sensors which we want to activate, number of the and we want to deactivate. Like you can see pin number 13 is activated, pin number 15 is activated. Using simple transistor transistor circuits, so we are controlling the power effect. So this was the fifth object. So fourth object. Now fifth object is to perform the results testing. So from here you can see how we perform the results. So basically the first task was the obstacle avoidance. So let's check the results. So you can see in this task, the robot has to perform turn left from here, but it's just slightly avoiding the from a bit delay. Then there is a line following task. You can see it's then there is a light seeking robot. In this robot task, we give it light source and then it stop and turn left. It has to turn left. So objective was achieved in both cases. So the what sort of feature recommendation for this kind of robot? We highly recommend you use small size high torque stepper motor for more precision. And to make it more compact, you should use small size SMD or small size ultrasonic sensors and complete circuit and design a complete circuit board which contain all the sensors. Like in case of a robot, we see we design all the floors with acrylic sheet. But I will suggest you to use first floor of that of PCB board, which contain all the cables, including VCC and ground. It will reduce the wire weight and make it more bulky, less bulkier. Use same lithium-ion battery and use color sensors to perform line following of different color, which is also a leading concept of STEM education. So these were the references. We have so far studied different papers, different research paper. We first study the research, then we get feedback from different students. Then we start our project. So thank you very much for your time. Please follow and like us EC Bio YouTube channel. And thank you very much for your time.